Hello everyone, chain rule. Okay, one of my favourite rules and something that we're going to be really stepping up to. I mean, I want us to work towards doing something like differentiating y equals ln of cos tan sec 3x squared, something like that, something really juicy, right? Function within a function within a function within a function within a function. Lovely stuff. But how do we get to that point? Well, I guess like with all things, we need to start from the beginning. So we know what the chain rule is. We know that the chain rule is if we have, so if y equals a function, so fg of x, a function within a function, right? Function within a function. We know that dy by dx is going to be g dash of x times f dash of g of x. Or if you prefer, and lots of people do, if we have y, then we're going to say that dy by dx is the same as dy by dt times by dt over dx, which is exactly the same thing as this actually. Because remember when we proved it, if you watch that video, that in that case we let t be g of x and we let f of t then be our y value. So let's stick with, I think the easiest way to stick with this is this. We're going to start using this and then we're going to slowly move away from, well, very quickly move away from it actually, because I don't want you using t's and stuff anymore. So here we go. We're going to use that definition. So let's look at, for example, y equals cos 3x plus 2. Okay, at the moment, looks pretty difficult, but we know that cos, for example, differentiates, so d by dx of cos differentiates to minus sine x. Okay, that's a good start. So if I let t be 3x plus 2, I'm now saying that y equals cos of t. Now, if we differentiate y with respect to t then, so dy over dt, because this variable t is the same as this is a function of t, cos is a function of t at the moment, then it's fine. We can differentiate this as normal. So as we've said, cos x with respect to x goes to minus sine x, so therefore cos t with respect to t goes to minus sine t. And remember, we're following this chain rule here. So we've got our first ingredient, dy by dt, and now we need to get our second ingredient, which is differentiating our t value with respect to x then. So if t equals 3x plus 2, we should get dt by dx is 3. And therefore put them together, dy by dx is going to equal dy over dt times by dt over dx. So we end up with minus 3 sine. We didn't start with t, so we're not going to finish with t. Remember, t is 3x plus 2. And we're happy. Notice then that what we did was we essentially, I want you to start thinking about this. We started with like cos x, but x in this case, or t in this case, was 3x plus 2. We then differentiated it as if it was cos x, but remember x in this case is 3x plus 2, so it went to sine x, and then we differentiated our x, which went to 3. Okay, let's do that again. Right, let's try something else then, same fashion. So let's go for y equals 3x squared plus 4 all to the power of 5. And let's use the chain rule. We've got a function within a function, yeah? If 3x squared plus 4 was our function, so like before, if we let t be 3x squared plus 4, you can see that y is a function t within a function to the power of 5, okay? Why am I using chain rule? Well, because obviously I do not want to be binomially expanding this thing and then spanning that bracket 5 times. That would take me ages. And imagine if it was a bigger number, 20 to the power of 100, whatever. The chain rule is going to fix this right out, and very simply. So we'll do what we did before. dy by dt then is then 5t to the 4. dt by dx is 6x, and therefore put them together, dy by dx is the same as dy by dt times by dt by dx. We didn't start with t, so we can't finish with t, times by 5, 6x, and we end up then with 30x, 3x squared plus 4 to the power of 5, and we're happy. Again, I want us to start not using t's anymore, because the more variables we use, especially as we use product and quotient rule, the more variables we use, the more confusing it can get. So I want us to start thinking about this in shortcuts then. So we'll do the shortcut version. 3x squared plus 4 all to the power of 5. To me, this reads x to the power of 5. That's what I see. So dy by dx is going to be x to the power of 5 differentiated. So 5x to the power of 4 then. And then we need to differentiate out x, which goes to 6x. See, it's exactly the same thing, it's just a lot quicker. And potentially less room for error if you're differentiating loads of things. Let's go again. Loads of examples then, loads of examples to get your head around it. Let's go for, this time, y equals sine 5x cubed plus x squared all to the power of 3. So when you're using trig functions to a power, it's much more helpful to write this with the power on the outside in big brackets, like you would on your calculator. It's just convention for trig to put your power here, but putting it out here makes more sense. Make sure you got the big brackets, otherwise you're looking at the angle all cubed. And this way, you can see it's more obviously a function within a function within a function. So we've got 3 sets here to deal with. But no matter, it's always exactly the same principle if we do it the quick way. So I'm going to do it the quick way. I don't want to be using t's, because you see you're going to get sine t all cubed, and then I have to make this thing be a u or something, say that u equals sine t, so then finally I get u cubed. You see, I'm going to have 3 sets of variables. It's going to start getting really confusing. We don't need to do that anymore. I mean, the maths is in place, we've proved everything, we know it works, but let's use that previous logic of saying let this be x. So in my head I'm going, that's x cubed. So x cubed differentiates to 3x all squared, times by, now we've got our differential of x, but here we have sine x, and sine x goes to cos x, but again we need to differentiate our x inside. You see, it's like Russian dolls. So 15x squared, they just keep opening up and opening up. And there we go, we've got our final answer. So 15x squared plus 2x, all times cos 5x cubed plus x squared, sine squared, that can come back in now, cubed plus x squared, and we're finished. It's looking pretty good. So remember, this is dy by dx then, and this is dy by dx. How do we check? Well, this is where the silver calculator comes in. If we go, make sure your calculator's in radians, remember, because all trig stuff needs to be differentiated using radians. When we prove that using the squeeze theorem, we use radians. So therefore, we use the sector formula, the area of a sector. So if we check, silver calculator, whack in x equals 0.01 into your answer here. You know, it's going to take a little bit of work on this one, but if you do 0.01 answer button, in fact I'm going to do that now, I'm going to force myself to do it as well. So calculator in radians, 0.01 equals, I'm whacking it into my answer, so 3 15 answer squared plus 2 answer times by cos 5 answer cubed, 5 answer cubed plus answer squared, close that bracket, and then we're timesing that by, remember, sine 5 answer cubed plus answer squared, and this is all squared. Careful where you put in your squared values. And we should get 7.111124935 all times 10 to the minus 10, so it's a tiny number. Let's put that into our original. So what I got to do is real easy with my silver, well, or any graphical calculator, right? So remember our original was sine cubed 5x cubed plus x squared. I just need to go, if I've got the silver calculator, shift integral button, you've got that d over dx thing there, so I'm going to put bracket sine 5 alpha x all cubed plus alpha x squared, and everything within there is to the power of 3, so make sure that you've got your bracket system right. So everything is to the power of 3. 1, 2, 3, 1, 2, 3. And then what we're going to do is, where it says what x value we want, we're going to put that as 0.01, just like before. So 0.01, and lo and behold, we do get our 7.11111, and we're happy. Alright, last one, so challenge 1. It'd be really cool if you could try this out. So why not try y equals, and we can do this quick. So why do I like 3 so much? Let's try. So you can pause the video in a sec, okay? 4x to the power 5 plus x all to the power of 20. Let's try sine of, so 3 sine x plus, let's put a tan x in there. Ooh. X plus tan x as your function in there, and also try cos of 3x cubed plus 5, and this is to the power of 4. Okay, so stop the video, pause it, and have a go by yourself. I give you 5 seconds. 5, 4, 3, go on, pause it. 2, go on, try it yourself. 1. Okay, cool, I'm glad you tried. So let's whiz through what's our answers. So dy by dx, for me that's x to the power of 20, so that's 20x to the power of 19, and this is all times the derivative of this x now, so that's 20x to the 4 plus 1. Done, we're happy. Check that. Make sure you've checked before you've looked at my answers. You should be checking this stuff. Dy by dx here, we're going to have, here's our sine, so to me that says sine x, and we know this is going to go 3, the 3 stays, cos x times by now the derivative of our inside, so this is our new x, so 1 plus sec squared x, remember tan differentiates to sec squared, and that's done. Make sure you've checked that. I have. So dy over dx this time for number 3 is cos to the 4. Remember how we write that? We're going to write that cos 3x cubed plus 5 all to the power of 4. Put that bracket on the outside. So to me that reads x to the 4. So we're going to get 4 cos 3x cubed plus 5. Power comes down, subtract 1 from the power, so that's 3. Now I've got cos x in there, which I know goes to minus sine x. And then I've got to differentiate my x, which will be 9x squared, and there we go. So if I just tidy that up, minus 36x squared cos cubed 3x cubed plus 5 sine 3x cubed plus 5, and done. Check it, make sure you're checking it, and we should be happy.